We are going to use XGBoost regressor to predict the stock returns in the following 2 days. I did not see much notebook here. Let me know if it is improper to post this note. The key ideas in this work are: 1. Using XGBoost to pre-select the 10 most important features to fight overfitting. 2. Using the linear loss function instead of the conventional square loss function. The final model consistently outperforms the all-zero predict. In my test, the model also performed better than the median prediction and could rank 30th in the private leaderboard. The testing data are also loaded to a data frame in Pandas. This code is similar to the previous one but with a different zip file and a different CSV file. First, it creates a new instance of the zip file class, specifying the path to a zip file called test_2.csv.zip located in the directory /input/the Winton stock market challenge/. Using the open method of the zip file instance, it opens the file test_2.csv inside the zip file. Then, it uses the read_CSV function from the Pandas library to read the contents of the test_2.csv file into a new Pandas data frame. The data frame is assigned to the variable new_df. Finally, the code displays the first few rows of the data frame using the head method, showing a preview of the data in the test_2.csv file. Data visualization and feature analysis. We load and visualize the data in the section. We also analyze the correlations between the features. To load the zipped data, we use the zip file package. The training data are loaded into a data frame in Pandas. This code imports several libraries, NumPy, Pandas, TensorFlow, and Matplotlib, that are commonly used in data analysis and machine learning tasks. Next, it imports the zip file class from the zip file module. This class is used to handle zip files. The code then creates an instance of the zip file class, specifying the path to a zip file called train.csv.zip located in a directory /input/the Winton stock market challenge/. Using the open method of the zip file instance, it opens the file train.csv inside the zip file. After that, it uses the read_CSV function from the Pandas library to read the contents of the train.csv file into a Pandas data frame. The data frame is assigned to the variable df. Finally, the code displays the first few rows of the data frame using the head method, showing a preview of the data. Here is an example of a strong correlation between two independent variables. In simple terms, the code runs a sequence of operations to generate a scatter plot using Matplotlib. Initially, the plt.scatter function is used to plot a scatter graph. The values for the x-axis are sourced from the feature_3 column of the data frame df, while the y-axis values come from the feature_11 column. The marker parameter is assigned the value O to utilize circular markers, and the S parameter is set to 1 to specify the size of these markers. Next, the title of the plot is set with plt.title, labeling the content as correlation between feature_3 and feature_11. The plt.label function is used to set the x-axis label, indicating that the values represent feature_3. Similarly, the plt.label function is used to set the y-axis label, signaling that the values represent feature_11. The final operation is to display the plot using plt.show. The resulting scatter plot depicts the relationship between the values of feature_3 and feature_11. Each data point is represented by a small, circular marker. The x-axis position of a marker corresponds to the value of feature_3, and its y-axis position corresponds to the value of feature_11. This scatter plot facilitates visual analysis of any correlation or patterns between these two features. Most of the columns contain missing values. Below are the top 10 features with the most missing values. This code creates a bar chart using the Matplotlib library to visualize the missing values in a data frame, df. First, it creates a figure, fig, and an axis object, ax, using the subplots function. The fig size parameter specifies the size of the figure, setting it to 15 units wide and 5 units tall. Next, it calculates the proportion of missing values in each column of the data frame by dividing the sum of null values by the total number of rows. This is done using the isNull sum, len-df expression, and the resulting series is assigned to df_na. Then, it drops the columns from df_na where the missing value ratio is 0, using df_na equals 0. Index. The remaining values are then sorted in descending order using sort_values ascending equals false, and the top 10 values are selected using 10. The resulting series is still assigned to df_na. After that, the code plots a bar chart using the x.bar function. The range df_na.size provides the x-coordinates for the bars, df_na provides the heights of the bars, and width equals 0.5 sets the width of the bars. The plt.sticks function is used to label the x-axis tick marks with the index of df_na, while rotation equals 0 sets the rotation angle of the labels to 0 degrees. plt.alim0, 1, sets the limits of the y-axis to be between 0 and 1. The code then adds a title to the chart using plt.title, sets the y-axis label using plt.label, and finally displays the chart using plt.show. The chart provides a visual representation of the top 10 features in the data frame that have the most missing values, with the missing ratio shown on the y-axis. The following presents 3 instances of the stock return time series within the initial 120 minutes of the current day. It's evident that different stocks can exhibit greatly varying behaviors. A thorough analysis of these time series can provide invaluable insights into the volatility of these stocks, which is extremely beneficial when pricing stock options. Nonetheless, the detailed intricacies within the time series tend to be too noisy to effectively predict average stock returns. As previously mentioned, we instead choose to aggregate the returns within the time series, representing them as a singular feature. The code carries out a sequence of operations to generate a line plot using matplotlib, which can be described in plain English as follows. The first step involves creating a figure, named fig, and an axis object, named ax, using the subplots function. The size of the figure is defined by the fig size parameter, which is set to be 10 units wide and 5 units tall. Next, a line graph is plotted using the plt.plot function, representing the returns of the first stock. This is achieved by using the first row, ds0, smiles of the ds array. A label is assigned to this line for the legend using the label parameter. Following this, the code plots another line graph representing the returns of the second stock. This line corresponds to the second row, ds1, smiles of the ds array. Subsequently, a third line graph is plotted for the third row, ds2, smiles of the ds array, which represents the returns of the third stock. The y-axis limits are then set using the plt.alim function to display values between -0.004 and 0.004. Similarly, the x-axis limits are set using plt.slim to show values ranging from 0 to 118. The y-axis label is set using plt.label, indicating that the values represent stock returns. In parallel, the x-axis label is set using plt.slabel, indicating that the values correspond to minutes. The title of the plot is set using plt.title, describing the content as examples of the stock returns in the first 120 minutes of the current day. A legend is added to the plot using plt.legend, which helps differentiate the lines representing each stock. Finally, the plot is displayed using plt.show. The resulting plot provides a visual representation of the stock returns over time for 3 distinct stocks, enabling an analysis of their respective patterns and fluctuations during the first 120 minutes of the current day. The stock returns in the following 2 days are split to 2 target variables. The code carries out several operations to isolate specific columns from the target label arrays, including y_train, y_val, y_test, y_train_val, and y. Firstly, it assigns the data from the initial column of the y_train array to the variable y1_train, which symbolizes the target labels for the first output. Likewise, the information from the second column of the y_train array is allocated to the variable y2_train, representing the target labels for the second output. The values from the first column of the y_val array are assigned to the variable y1_val, indicating the target labels for the first output in the validation set. Similarly, the data from the second column of the y_val array is allocated to the variable y2_val, which stands for the target labels for the second output in the validation set. The code assigns the values from the first column of the y_test array to the variable y1_test, embodying the target labels for the first output in the test set. The values from the second column of the y_test array are allocated to the variable y2_test, representing the target labels for the second output in the test set. The values from the first column of the y_train_val array are assigned to the variable y1_train_val, denoting the target labels for the first output in the combined training and validation set. The data from the second column of the y_train_val array is allocated to the variable y2_train_val, symbolizing the target labels for the second output in the combined training and validation set. Finally, the values from the first column of the y array are designated to the variable y1, indicating the target labels for the first output in the original dataset. The values from the second column of the y array are allocated to the variable y2, representing the target labels for the second output in the original dataset. Overall, these operations isolate specific columns from the target label arrays, enabling individual analysis or modeling for each output. For instance, y1_train contains the target labels for the first output in the training set, while y2_val carries the target labels for the second output in the validation set. We extract the minute-by-minute stock return time series from the independent variables. My initial approach was to utilize a recurrent neural network, RNN, to handle this time series data, but the RNN was prone to significant overfitting. As a resolution, I chose to aggregate all the returns in the time series, creating a single feature that reflects the stock return for the first 2 hours of the current day. In parallel, I experimented with numerous models to forecast the intraday stock return time series. However, none outperformed a simple all-zero prediction. This makes sense, as in practical terms, our goal is to predict the stock return for the next minute only. Our model can be updated every minute with fresh data. Thus, I'll employ the all-zero prediction for intraday stock returns, focusing my efforts on predicting the stock returns for the subsequent 2 days. The code in question carries out a series of operations, simplistically explained as follows. The first action is to compute the sum of values for each row across the columns marked red_2 through red_120 within the data frame df, with the resulting sum stored in a variable named retired. It then executes a similar operation on the data frame new_df, again summing the values of each row across the red_2 to red_120 columns and storing the outcome in a variable called new_retired. The code then merges the values from columns feature_1 to red_-1 in df with the values in the ret variable. This amalgamation is done using np.stack, and the combined values are stored in a variable named x. The next step involves extracting values from the red_2 to red_120 columns in df, storing them in a variable known as ds. Additionally, the code extracts values from columns red_+1 and red_+2 in df, which are stored in a variable named y. Further, it takes values from red_121 to red_180 columns in df and stashes them in a variable called y_ds. Following a similar pattern to the third operation, the code combines the values from the feature_1 to ret_-1 columns in new_df with the values in new_ret using np.stack. The resulting combination is stored in a variable named new_x. In its final act, the code extracts values from the red_2 to red_120 columns in new_df, storing the extracted values in a new_ds variable. On the whole, these operations are associated with data manipulation and extraction. The newly created variables will be subsequently used for further data analysis or modeling tasks. Since we do not know what those independent variables stand for, we just impute the missing values with the mean of that feature. If we are in a real world knowing the meaning of those independent variables, we may find better imputation methods. The code carries out a series of operations using the simple imputer class from the scikit-learn library, which can be explained in plain English as follows. The first step is to import the simple imputer class, a tool used to handle missing values within the dataset. Subsequently, an instance of this class is created, with the strategy parameter set to mean. This implies that any missing values will be filled with the corresponding feature's mean value. Next, the instance of simple imputer is applied to the array x through the fit_transform method. In practical terms, this means that any missing values within x are replaced with the mean value of their corresponding feature. This process is then repeated with the array new_x, but with the transform method of the simple imputer instance. Here, missing values in new_x are replaced with the mean value of their respective feature, based on the mean values calculated from the x array. In a similar vein, the fit_transform method of the simple imputer instance is applied to the ds array. This operation replaces any missing values in ds with the mean value of the corresponding feature. Following the same pattern as with new_x, the transform method of the simple imputer instance is applied to the new_ts array. In this case, missing values in new_ts are replaced with their respective features' mean value, which is calculated based on the mean values derived from the ts array. In summary, the code employs the simple imputer class to fill in any missing values within the given arrays, x, new_x, ts, new_ts, using the mean value of each feature. This step is crucial in ensuring that the data is complete, thereby making it ready for subsequent analysis or modeling tasks. The data are split into training data, validation data, and testing data. From the discuss section of this challenge, we know the feature _7 is closely related to the time. Therefore, we do not use cross-validation or random splitting here. Otherwise, future information will leak into the training data, and we will get a model that performs very good on the training data but is not useful in predicting future unseen data. The code executes several operations to divide the data into various subsets. Firstly, it designates the initial 30,000 rows of the array x to the variable x_train, serving as the training data. Next, rows 30,000 to 35,000, excluding the 35,000th row, of the array x are assigned to the variable x_val, which represents the validation data. Then, rows commencing from the 35,000th row of the array x are allocated to the variable x_test, standing for the test data. Similarly, the first 30,000 rows of the array y are assigned to the variable y_train, representing the target labels for the training data. Rows 30,000 to 35,000, excluding the 35,000th row, of the array y are assigned to the variable y_val, serving as the target labels for the validation data. Rows starting from the 35,000th row of the array y are allocated to the variable y_test, symbolizing the target labels for the test data. Furthermore, the initial 35,000 rows of the array x are designated to the variable x_train_val, symbolizing the consolidated training and validation data. Correspondingly, the first 35,000 rows of the array y are assigned to the variable y_train_val, which signifies the combined target labels for the training and validation data. In essence, these operations successfully partition the original dataset, x and y, into separate subsets for training, validation, and testing. The training set encompasses the first 30,000 rows, the validation set comprises rows 30,000 to 35,000, and the test set includes rows starting from the 35,000th row. Additionally, there's a combined training and validation set, x_train_val and y_train_val, that embraces the first 35,000 rows of the original dataset. The subsequent figure illustrates the significance of each independent variable in constructing the decision trees within the XGBoost regressor. The most impactful feature is F6, which corresponds to feature _7 in the original data. The next three most significant features, F25, F26, and F27, represent the stock returns from the past 2 days and the current day. Given that the independent variables have minimal correlation with the target variables, incorporating all of them would introduce considerable noise into our model. To mitigate this, we have chosen to only use the 10 most important independent variables in our predictive model. The code executes several operations utilizing this XGBoost library. Firstly, it employs the XGB.train function to educate an XGBoost model, labeled as XGB_med. The parameters defined in the param dictionary, the trained matrix as the training data, and the num_boost_round set to the quantity of boosting rounds or iterations, defined by the shape of BST, the results from cross-validation, are all used in this process. This trains the model with the optimal number of boosting rounds as determined by the cross-validation process. Next, it uses the subplots function to generate a figure, designated as fig, and an axis object, termed ax. The size of the figure is defined by the fig size parameter, setting it to a width of 6 units and a height of 8 units. The xgb.plot_importance function is then invoked to depict the significance of features based on the trained XGBoost model, xgb_med. The ax parameter specifies the axis object where the importance will be plotted. Finally, plt.show is called to display the plot. The resulting diagram illustrates the importance of various features in the trained XGBoost model. Higher importance scores are given to features that contribute more to the model's performance. This diagram aids in identifying the most impactful features and offers insights into their effects on the model's predictions. Here is an example of one decision tree inside the XGBoost model. It has only one leaf. The code carries out several operations utilizing the XGBoost library. Initially, it creates a figure, denoted as fig, and an axis object, identified as ax, using the subplots function. These objects will be employed for the visual representation of the tree structure. Next, the XGB.plot_tree function is invoked to visualize the decision tree structure of the XGBoost model that has been trained, XGB_med. The axis object, in which the tree will be plotted, is defined by the ax parameter. Finally, plt.show is used to display the tree visualization. The resulting plot illustrates the structure of the decision tree within the trained XGBoost model. Each node symbolizes a decision or a feature split, while the edges represent the decision-making flow based on the values of the features. This visual representation provides insights into the decision-making process of the model and the hierarchy of feature importance within the tree. Below is the mean absolute error, MAE, of the training data and validation data during the training. The code executes several operations to create a figure consisting of two subplots using matplotlib. Initially, it generates a figure, labeled fig, with dimensions of 12 units in width and 4 units in height. The main title of the figure is set as the mean absolute error, MAE, of the training data and validation data using the fig.subtitle function. The first subplot, plt.subplot121, is created on the left side of the figure. Two line graphs are plotted on this subplot using plt.plot to display the MAE values of the training and validation data. The X values are extracted from the train MAE mean and test MAE mean keys in the BSD dictionary for the training and validation data respectively, with the corresponding MAE values as the Y values. Labels train and validation are assigned to these lines for identification. The X-axis label is set as the number of runs, and the Y-axis label as the MAE, using the plt.label and plt.label functions respectively. A legend is added to the subplot using plt.legend for differentiation between the training and validation data lines. The second subplot, plt.subplot122, is created on the right side of the figure. This subplot replicates the line graphs from the first subplot, displaying the MAE values of the training and validation data. However, the Y-axis scale is set to logarithmic using plt.escalelog. The X-axis and Y-axis labels are set similarly to the first subplot, and a legend is also added. Finally, the plt.subplots_adjust function is used to adjust the spacing between the subplots, creating some separation. The figure with the subplots is then displayed using plt.show. The final figure consists of two side-by-side subplots, each illustrating the trend of MAE values for the training and validation data across the number of runs. The first subplot presents the MAE values on a linear scale, while the second depicts them on a logarithmic scale. This visual representation allows for a comprehensive comparison of the training and validation errors throughout the model training process. We illustrate the correlations among various features in the data. Some independent variables exhibit strong interrelations. This aspect will be further discussed in the subsequent two cells. We also observe that the target variables demonstrate negligible correlation with the independent features. This suggests that it might be challenging for our model to surpass basic predictions, such as the all-zero prediction and the median prediction. The code executes a series of operations to construct a correlation heat map using the mlextend library, which can be explained in layman's terms as follows. Initially, the code imports the heatmap function from the mlextend library's plotting module. Following this, it computes the correlation matrix, denoted as CM, using the np.corcof function. This matrix is derived from the stacked values of X, the input features, and Y, the output labels, after they've been transposed. Subsequently, a list of column names, referred to as cols, is created. This list combines the column names of df from index 1 to 28, and appends three additional labels, ret, ret_+1, and ret_+2. These extra labels symbolize the output labels. The code then invokes the heatmap function, feeding it the correlation matrix, CM, as the primary data. It also defines the row names and column names through the row_names and column_names parameters, respectively. The size of the resultant heatmap is set to 20 units by 20 units using the fig size parameter. The title of the plot is set with plt.title, describing the content as correlations between the different features of the data, and the font size is defined as 20. Finally, the plot is exhibited using plt.show. The end product is a heat map that visually delineates the correlations between various data features. The heat maps rows and columns represent the features, while the color of each cell demonstrates the strength and direction of the correlation between the corresponding features. This facilitates easy detection of patterns and relationships within the dataset. The final models are trained on the unions of the training data and the validation data. The provided code executes the following operations. Firstly, it fits the best_XGBR model, an instance of the XGBoost class with optimized parameter settings, on the combined training and validation data, x_train_val, y1_train_val. This step trains the model using the features, x_train_val, and the corresponding target labels, y1_train_val, enabling it to learn the underlying patterns and relationships in the data. Next, the trained best_XGBR model is employed to make predictions, y1_test_pred, on the test data, x_test. By utilizing the learned patterns from the training and validation data, the model generates predicted values for the target variable, y1, based on the provided test features. Subsequently, the same best_XGBR model is refitted on the combined training and validation data, x_train_val, y2_train_val, but this time for the second target variable, y2. This allows the model to learn the pattern specific to the second target variable. Finally, the trained best_XGBR model is utilized once again to predict values, y2_test_pred, on the same test data, x_test, but this time for the second target variable, y2. These predictions are made based on the patterns and relationships learned from the training and validation data. In summary, the code trains the best_XGBR model on the combined training and validation data for both target variables, y1 and y2. It then leverages the trained model to predict the values of the target variables, y1_test_pred and y2_test_pred, on the test data, x_test. This process allows for evaluating the model's performance and assessing its ability to generalize to unseen data points. Here is an example of using the utility function to tune the maximum depth of the tree and the minimum child weight. The tuning of other parameters are omitted here for brevity. The provided code performs a parameter search for an XGBoost model. It begins by defining a dictionary named param that holds various parameter settings for the XGBoost model, such as the learning rate, verbosity, objective function, tree construction method, number of estimators, number of jobs, gamma value, subsampling ratio, column subsampling ratio, and regularization parameter alpha. These settings determine how the model is trained and how the decision trees are constructed. Two additional dictionaries, param1 and param2, are defined to specify the ranges of values to search for two specific parameters, max_depth and min_child_weight. These parameters control the depth of the decision trees and the minimum weight required to create new tree nodes, respectively. By defining different values for these parameters, the code enables the exploration of different configurations of the XGBoost model. The code then calls them a search function, passing the training and validation data, x_train, y1_train, x_val, y1_val, the initial parameter settings, param, and the parameter search dictionaries, param1 and param2. The msearch function conducts the parameter search, evaluating various combinations of parameter values, and returns the best score and the corresponding best parameter values that achieve the optimal performance according to the specified evaluation metric. Finally, the code prints the best score and best parameter values obtained from the parameter search. This allows the user to observe the parameter combination that yielded the highest performance on the given training and validation data. In summary, this code aims to find the best combination of parameter values for an XGBoost model by performing a search over specified ranges. The goal is to determine the parameter settings that result in the highest performance according to the evaluation metric. Here is the final parameters after all tunings. The code in question instantiates the XGBoost class from the XGBoost library, setting specific parameters to construct an XGBoost regression model. Let's delve into each parameter to better comprehend their roles. An instance of the XGBoost class is assigned to the variable best_XGBR, symbolizing the XGBoost regressor model configured with the defined parameters. The red pseudo-Huber error is assigned to the objective parameter, implying that the pseudo-Huber loss function will guide the model's training. This loss function is adept at handling outliers, making it more effective for regression problems than other loss functions. The tree_method parameter is allocated the valued poo_hist, enabling the usage of the graphics processing unit, GPU, for efficient computation of decision trees, significantly accelerating the training process if a GPU is available. The max_depth parameter is set to 5, defining the maximum depth of the decision trees in the model. Higher values allow for the capture of more complex data relationships, but also increase the risk of overfitting. The min_child_weight parameter is set to 3, specifying the minimum weight necessary for the creation of a new tree node during model training. This parameter helps control overfitting by inhibiting the creation of nodes with low weights. The gamma parameter is set to 0, representing the minimum loss reduction required for further partitioning of a tree leaf node. This parameter provides regularization by managing the model's complexity. The subsample parameter is set to 0.9, specifying that each boosting round will randomly select 90% of the samples. Known as stochastic gradient boosting, this strategy reduces overfitting by training the model on different data subsets. The call_sample_by_tree parameter is set to 0.9, indicating that 90% of the features will be randomly selected for each boosting round, introducing feature subsampling and further reducing overfitting. The alpha parameter is set to 0, denoting the L1 regularization term on the weights. It improves model generalization by discouraging large weights through the addition of a penalty term to the objective function. The learning_rate parameter is set to 0.01, controlling the step size shrinkage used during each boosting iteration. A smaller learning rate results in slower learning, requiring more iterations but providing better generalization. The n_estimators parameter is set to 700, defining the maximum number of boosting rounds, iterations, for the model. It determines the number of individual decision trees that will comprise the ensemble. Thus, by setting these parameters, the code creates an instance of the XGBoost class, representing an XGBoost regression model with the specified settings. This model can then be trained on a dataset and employed to make predictions on new data points. We final train the models on the whole data and make prediction on the unseen data. The given code conducts a series of operations using the best_XGBR model, which is a configured instance of the XGBoost class. To begin with, this model is fitted using the selected features, x, select, and the target variable, y, 0, corresponding to the first target variable, y1. Upon training the model, it is then utilized to predict the values for the first target variable, y1, generating a set of predictions termed as y1_new_pred. These predictions are obtained by applying the model on the selected features from a new dataset, referred to as new_x, select. The code proceeds to refit the same best_XGBR model, but with a change in the target variable. This time, the selected features, x, select, and the second target variable, y1, pertaining to y2 are used. Post-training, the best_XGBR model is again employed, this time to predict the values for the second target variable, y2. This results in another set of predictions, y2_new_pred, which is derived using the selected features from the new dataset, new_x, select. To sum up, the code harnesses the trained best_XGBR model to generate predictions on new data for two target variables. This involves fitting the model separately with selected features and the respective target variable for each target variable. Subsequently, it predicts the values for both target variables using the selected features from the new data. This strategy facilitates the generation of predictions for new data based on the trained model. Feature selection with XGBoost. We use a preliminary XGBoost regressor to do feature selections in this section. The NumPy array are transformed into a matrix to be compatible with the XGBoost package. The code conducts several operations using the XGBoost library. Firstly, it imports the XGBoost library, assigning it the alias XGB. Next, it formulates a matrix, labeled train, from the training data, x_train, and the corresponding target labels for the first output, y1_train. A matrix is a data structure specifically designed for XGBoost, optimized for performance and efficiency. Subsequently, a dictionary, named param, is defined. This contains various parameters to configure the XGBoost model. Key parameters include verbosity, which controls the verbosity of the output messages, set to 0 to suppress, objective, specifying the loss function to be optimized. Here it is reg pseudo-uber error, the pseudo-Huber loss for regression problems, a val_metric, which sets the evaluation metric used during training, in this case, may or mean absolute error. Other parameters such as subsample and colsample_bytree control the sampling of training data and features respectively to prevent overfitting. Tree_method stipulates the tree construction algorithm, with GPU_hist signifying the use of a GPU for computation if available. Parameters like eta, max_depth, gamma, min_child_weight are hyperparameters controlling the learning rate, tree depth, regularization, and the minimum weight required to create a new tree node. Finally, the XGB.CV function is called to conduct cross-validation with the defined parameters. The param dictionary, the trained matrix, and other parameters are passed as arguments. Then fold parameter establishes the number of folds for cross-validation, 3 in this case. The num_boost_round parameter indicates the maximum number of boosting rounds, iterations, and the early_stopping_rounds parameter determines the number of rounds with no improvement after which training will cease. The result of the XGB.CV function is assigned to the variable BST, representing the trained XGBoost model with cross-validation. Model training with XGBoost regressor Pilcrow. In this section, we meticulously train a XGBoost regressor, taking note that we employ the pseudo-Huber loss function, which serves as a differentiable approximation of the linear loss function. Compared to the traditional square loss function, it exhibits a lower sensitivity towards outliers, a critical factor contributing to the superior performance of our model. Initially, we establish a utility function to execute grid search for parameter optimization. This utility function is capable of adjusting parameters on both one-dimensional and two-dimensional grids. The provided code defines a function called MaSearch that conducts a parameter search and provides the optimal score and corresponding parameters based on a specified estimator and evaluation metric. To begin, the code imports the necessary modules, the XGBoost class from the XGBoost library and the mean_absolute_error function from the scikit-learn metrics module. The MaSearch function takes several input parameters, including the training and validation data, x_train, y_train, x_val, y_val, an initial set of parameters for the estimator, param, dictionaries containing values to search for specific parameters, param1 and param2, the estimator class to use, estimator, and the evaluation metric function, score. Within the function, it initializes the best_score variable to a high value and creates a copy of the param dictionary called best_param. Next, it extracts the keys from the param1 and param2 dictionaries to identify the names of the parameters to be searched. If param2 is not none, the code enters a nested loop that iterates through the values of param1 key 1 and param2 key 2. It assigns the current parameter values to the para dictionary and creates an instance of the specified estimator class with these parameters. The estimator is then fitted to the training data, and the target labels are predicted for the validation data. The current score is calculated using the specified evaluation metric. If param2 is none, the code enters a loop that iterates through the values of param1 key 1. It assigns the current parameter value to the para dictionary, creates an instance of the specified estimator class with this parameter, and fits it to the training data. Predictions are made for the validation data, and the current score is calculated. Throughout the loops, the current score is compared to the best score achieved so far. If the current score is lower, indicating better performance, the best score is updated, and the corresponding parameter value is stored in the best_param dictionary. Once the parameter search is complete, the function returns the best score and best parameters as a tuple. We select the 10 most important independent variables. The code is designed to execute a series of operations to cherry-pick specific columns from the feature matrix, denoted as X. To begin with, it defines a list, named select, which holds the indices of the columns intended for selection from X. The selected indices are 1, 5, 6, 13, 14, 18, 22, 25, 26, and 27. The selected columns, extracted from the initial 30,000 rows of X, are then assigned to the variable x_train. This operation generates a new feature matrix for the training data, which only encompasses the columns specified in the select list. Subsequently, the selected columns from rows numbered from 30,000 to 35,000, excluding the 35,000th row, of X are designated to the variable x_val. This action creates a new feature matrix for the validation data that solely includes the columns specified in the select list. Following this, the selected columns from rows commencing from the 35,000th row of X are allocated to the variable x_test. This operation crafts a new feature matrix for the test data, which only includes the columns specified in the select list. Lastly, the selected columns from the first 35,000 rows of X are given to the variable X_train_val. This results in a new feature matrix for the combined training and validation data, exclusively comprising the columns specified in the select list. In summary, these operations effectively produce new feature matrices, X_train, X_val, X_test, X_train_val, that only retain the selected columns from the original feature matrix X. These selected columns can be harnessed for subsequent analysis or remodeling, thereby concentrating on the specific features of interest. We evaluate the model performance on the testing data. The final models consistently perform better than the all-zero prediction. Firstly, it imports the mean_absolute_error function from the scikit-learn library. This function will be used to calculate the mean absolute error, MAE, between the predicted values and the true values. Two lists, benchmark and fitted, are defined. The benchmark list contains the mean absolute error of the benchmark predictions, which is calculated as the absolute mean of the true values for Y1_test and Y2_test. The fitted list contains the mean absolute error of the predictions made by the trained XGBoost regressor model, Y1_test_pred and Y2_test_pred, compared to the true values in Y_test. The index array is created using np.arrange2, which generates an array with values 0, 1. This array will be used to set the x-axis positions for the bars in the bar plot. The bar_width variable is set to 0.35, representing the width of each bar in the bar plot. Using plt.bar, the code creates a bar plot with two sets of bars plotted side by side. The first set represents the benchmark predictions, all-zero prediction, and the second set represents the predictions made by the XGBoost regressor. The x-axis positions for the bars are specified using index and index plus bar_width, while the heights of the bars are determined by the values in benchmark and fitted. Labels are provided for each set of bars, all-zero prediction and XGBoost regressor. Using plt.sticks, the x-axis stick labels are set to red_+1, red_+2, indicating the stock returns in the 2 following days. The title of the plot is set to comparison of the XGBoost regressor and the all-zero prediction using plt.title. The x-axis label is set to stock returns in the 2 following days using plt.slabel, and the y-axis label is set to May of the prediction using plt.label. Using plt.elim, the y-axis limits are set to 0, 0.021, determining the range of values shown on the y-axis. A legend is added to the plot using plt.legend, specifying the labels for the 2 sets of bars, all-zero prediction and XGBoost regressor. Finally, the plot is displayed using plt.show. Ensembles of the XGBoost regressor and the median prediction are used for the final results. The median prediction are used here to reduce overfitting. The given code executes a sequence of operations, starting with the calculation of predicted values for the first target variable, denoted as Y1_new_pred. This is achieved by blending 10% of the predictions made by the best_XGBR model with 90% of the median value of the first target variable derived from the original data. Following a similar approach, the predicted values for the second target variable, referred to as Y2_new_pred, are computed. Here, 10% of the predictions from the best_XGBR model are combined with 90% of the median value of the second target variable from the original dataset. Next, the code initializes an empty array, termed ts_new_pred, with dimensions corresponding to the number of rows in new_x and 60 columns. This array is designated for storing predictions for the time series data. The subsequent operation involves accessing the sample_submission_2.csv.zip file through the zip file class and reading its contents into a pandas data frame called sub. This file is presumed to contain the requisite format for submitting predictions. The predicted column in the sub-data frame is then updated with the calculated predictions. These predictions include the concatenated arrays of ts_new_pred, y1_new_pred, reshaped into a single column format using np.newAxis, and an array constituted of the median value of the second target variable, repeated for each row in new_x. The final data frame, sub, can be exported as a CSV file, submission.csv, to submit the predictions. To sum up, The code utilizes the best_XGBR model to generate the predicted values for the target variables. By blending the model's predictions with the median values from the original data, the prediction accuracy is potentially enhanced. The prepared submission file is then updated with these predictions.